So today is going to be the last lecture on scanning. So we'll be talking about some implementation details about scanning. So now we know the concept. We know the concept of scanning. We write regular expressions, then we convert them into non-deterministic finite automata, then to deterministic finite automata. Then we will need to generate the code. We'll need to generate actual code that simulates that deterministic finite automaton or implements it. And that code, we can generate it. We can write it manually. You can do it by hand. You can do the whole scanning process by hand, and some compilers do it by hand, or in some compilers it's done by hand, meaning it's manually coded. And in other compilers, a scanner generator is used. And like we said last time, with the scanner generator, the scanner generator, like Lex or Flex, you just feed it the regular expressions, and it gives you the scanner code. And internally, it converts the regular expression to an NFA, then it converts it into a DFA, then it minimizes the DFA, then it generates the code. And today's lecture is going to be about about generating the code. This code that will get generated, given the DFA. We are given a DFA, a minimized DFA, and we would like to generate the code. And there are two schemes for this. We can do it either using tables, so it can be either table-driven, or it can be direct-coded. So let's talk about the table-driven. First. So in a table-driven, you will have a DFA like this. A DFA will be a two-dimensional table or a two-dimensional array, which will look like this. These are your states. So this is S0, S1 to Sn. And these are your symbols. So your symbols could be 0, 1, 2 through 9. And then you have the letters A, B through Z. And then you have all the different characters, like operators, for example, all the different operators and all the different characters that you can use in a program. So there will be a column for each one, and there will be a state. And the DFA is just a two-dimensional table. So if we are in S0 and we get a 1, we go to S2, for example, and so forth. Then the code will be based on this table. So the code will just say, OK, it will keep track of the state. And based on the current state, it will look up, based on the current state and the current character that it's reading from the input. So given the current state, which is initially S0, this is our start state. And based on the current character that we are seeing in the input, we look it up in the table and see what the next state is, and we move to the next state. And in these states, there are two. There will be a state that represents an error. The SE, or the error state. So the error state will be explicit in a DFA, because in a DFA, there will always be a transition. What an error state in the DFA may correspond to in the NFA is just no transition. So for example, if you have an NFA with this goes on A or B, and in this final state, if you get an A, you cycle. Then this implicitly means that if you get a B when you are here, then you go to some error state. So this is an NFA. And in the corresponding DFA, then if you get an A, you loop. And if you get a B, you go to an error state explicitly. So in the DFA, the error state is explicit. And we need this because we need to check if we have, if the string that we are scanning, if we are still matching or we stop to match. So remember the example from last time, if you have something like x, y, z, 1, 2 equals ABC. So when you have something like this, you keep matching. This matches with an identifier, matches. You are fine until you get to this. When you get to this, you no longer match. So it means that you have a transition to an error state. So to make this concrete, so for this, you will have a start state. Then for A through Z, you go to this state. And if you have A through Z or 0 through 9, you keep cycling. But if you get something else, anything else, you go to an error state. So when you are scanning this, the first X will take you to this, which is an accept state. Then the Y will keep you, the Z, 1, 2. You stay in this accept state until you see this equal. Then you go to an error state. And when you get to this equal, you know that now you have, this is the lexeme that you have matched. So this lexeme has been identified as an identifier. So this accept state, for every accept state, you need to label that accept state with a corresponding syntactic category. And the syntactic category in this case is, what's the syntactic category for identifier? Exactly. So this is an accept state. So for each accept state, there is a syntactic category, which is in this case identifier. So the idea is that we use this error state to detect that we no longer match. So after you reach this, now you need to, when you get to the error state, you need to backtrack to the last accept state that you visited. So in this case, you backtrack and you go to this last accept state, and you take this as the longest match. Remember last time we go for the longest match, right? We don't go for the first match. So in this case, this matches, but the longest match, the longest lexeme that matches one of the syntactic categories in the language here is this whole variable name. Okay, so once you hit the error, you go to the last accept state that you have found. And then once you do this and you recognize the lexeme and the corresponding syntactic category, you start over. Now you start over scanning from the equal sign. And you match it. Then you start over here. And the longest lexeme is going to be this. This will match an identifier. And so forth. OK, so now the point is that when you reach this error state, you know that you want to roll back to the latest accept state. The latest accept state may not necessarily be the last state. So sometimes you may want to go a few states back. In general, generally speaking, you may want to go a few states back. So that's why in a typical implementation, you put the states on a stack, and then in order to backtrack to go to the latest accept state, what do? You pop. You keep popping until you get to an accept state. So you keep putting all of these states until you get to the last. So in this case, for example, this is S1, this is S2, and this is SE. So on your stack, you will have S1, then S2, then S2 again, then S2 again, for 1, 2, 3, 4. So you have 4 S2s, then an SE. So when you get to the SE, you take the last accept state, and it's an S2. And you have to have a mechanism to determine whether a given state is an accept state or not. So in an implementation, this accept, each state may be represented by an object. And in this object, you have a field that indicates whether it's an accept state or not. Yeah?
Wouldn't there be 5 S2s? So you go to S2 for the one. So you initially enter S2 on the X.
Oh.
And then go back.
Okay.
1 and 2, so that's 5.
Yes. So yes, you are right. So there will be 5 of them in this case. Yeah, and S1 is not an accept state. Yeah. Okay. So the idea is that you wanna pop things off the stack, and you get to the latest accept state. And as we said last time, there may be multiple matches, which means that the accept state that you have may correspond to multiple syntactic categories. And in this case, you need a way for resolving this conflict. And one simple way of resolving this conflict is to give priorities to the different syntactic categories. And a simple way of specifying the categories is just to go by the order in which they are listed in the regular expression file, the file of regular expressions that you are inputting to the scanner generator, or that you are using to generate a scanner manually. Okay, so now having said that, there is one more thing that we need to say about the table-driven scanner before we write some pseudocode for a table-driven scanner. Here, there is some redundancy in this table. So where do you see the redundancy? So this table seems, is bigger than what it should be or what it could be. We can make some compaction. So what do you think the redundancy will be? So can you detect the redundancy in this table, or something that is taking unnecessarily more space than it should? Yeah.
Imagine in all the states, then all the numbers would have the same destination states. So maybe you could
exactly
have just the column for all the numbers.
Yeah. So all the numbers will be treated equally in most cases, and we will detect this by looking at this column. So if the states in this column, if this is for example, S3, S5, S9, and this is S3, S5, S9. So if two columns, sorry, I put this under 9, sorry. S3, S5, S9. So most likely, all of these characters will have the same transitions because they are treated equally. So if you have multiple columns that lead to the same transitions, then you can categorize the symbols of the alphabet. So you can categorize all of these as, the letter, call them, belong to the letter category. And then you have one transition for the letter category. And similarly for the digit. So you can do two tables. One table that takes a symbol and gives you the corresponding category. And then your actual transition table is based on the categories. So it could be something like this. So the categorization table, cat for categorization. So you may have something like, for example, 0, 1, 2, and these are all, or maybe let me make it a little bit bigger to write digit. 0, 1, 2. These are digits. Okay, and A, B, so these are letters. And then your actual transition table is going to be like this. So this is the transition table, which corresponds to the transition function. It's going to be like this. S0, S1, S2, and then here you have digit, letter, and there are things that you cannot categorize, like this is a category by its own. So it will have its own category. So it will appear in the category table, but its category is like semicolon or something. So here it's the semicolon category. And so there are symbols that will have their own categories, and there are symbols, multiple symbols that will get mapped to the same category. So this will obviously minimize the number of columns in the table. Yes?
What happens if we encounter a situation like, say, integers where we don't want leading zeros and it wants the, say, 0 but not the rest?
Okay, so if the 0 has a different behavior, then the column for 0 will not match the columns for the other digits. So it will have a different transitions. So in this case, the 0 will have its own category. So this will be the non-zero digits, and then 0 will have its own category. So you can put symbols in the same category only if they have identical transitions for all, in all cases, for all states. So if the corresponding columns are identical. Okay, so that's a good question. Now, so this is about having similar columns. We can get around this, or we can avoid having this redundancy in the table. Now, what's the price that we are paying here?
2 table lookups.
Yeah, exactly. 2 table lookups, and tables are in memory. So in this case, you are accessing memory twice. You are doing 2 table lookups, and this will, this can potentially be slower, but this is more space efficient. But sometimes space can affect speed. So using a lot of space can slow down your program sometimes. Why?
Caches.
Because of caching. Yeah, exactly. Sometimes using a lot of space means that your data set does not fit in the cache, which means a lot of slowdown. So sometimes space can make things slower. So it depends on the size of your cache and whether this is going to fit in your cache or not. Not only this, the whole data set, that your program is accessing at a given point or at a given phase. Okay, so let's now take this. Now, before we erase this, we just said that we can have identical columns. Can we have identical states?
Wouldn't that?
Identical rows, I mean?
Wouldn't the DFA minimization get rid of that?
Exactly. Yeah, that's exactly the answer. So it's if you don't do DFA minimization, then you may have identical rows. But if you do DFA minimization is about merging states that have identical transitions into one state. If there are multiple states that have identical transitions on all symbols, you merge them into one state. You identify them as equivalent states, and you merge them. So if you have done DFA minimization, if this is the minimal DFA, then you will not have identical rows, but you can have identical columns. OK. So let's now adopt the two-table lookup. So our table-driven scanner is going to be so this is the pseudocode. So initially, our state, so we have a variable that keeps track of the state. Our state is initially S0, so we'll always call our start state S0. Then our lexeme is initially empty, or this looks like blank. Let's make it empty, or just call it empty. Our lexeme, which is the string that we are x1, 2, 3 equals ABC. So in this case, our lexeme is initially empty. Then we will add x to the lexeme. Then we will add 1. Our lexeme becomes x1. Then it becomes x12, then x13. And the lexeme that we will end up matching in this case is going to be x123. OK. So now this is the state. Now we have to remember that stack. We have to push things on the stack. So we'll have a stack, and we will clear it first. Stack dot clear. Then stack dot push. We will push something on the stack to indicate that this is the start. So in this case, in that example, before we put S1, S2, S2, we can put some artificial state that indicates that, when we get to this, then we have reached nothing. So you can call it a null state. So we push a null state on the.
Why not use S0?
OK. Because you may get to S0 again, so you may go back to. So this could be S0,
Oh, okay.
S1, S2. Then you can go to S0 again. So when you pop and you get to this S0, this does not necessarily mean that you are right at the beginning of the lexeme, or that this corresponds to an empty lexeme.
Right.
OK. Then we will loop. Now our loop will be looping until we get to that error state. So while state is not equal to SE, so SE is the error state. OK. We will read a character. Character equals get next character. We read the next character, and then we add this character to the lexeme. So our lexeme equals lexeme plus character. OK. Then we haven't pushed S0, so we push the state dot push the state. There is something missing here that I will talk about in a minute. Then what should we do?
Transition.
So we have the character. What should we do next? So every time we're checking a character, every iteration of the loop is checking a character.
Shouldn't we check it in the Before we
Yeah.
put it in the lexeme, shouldn't we check it first?
Yeah, we put it, and then if it turns out that it will lead to an error state, we will roll back. So yeah, we put it to the lexeme now, and we will check it. We will check the categorization table. So our category is going to come from the cat table of the character. So it will tell us what the category is. Then what should we do next?
Look it up in the transition.
Look up the category in the transition table. So our new state is going to be, the transition table Okay, so cat table is the categorization table. And tx table is the transition table. So the transition table, in fact, this is going to be, because the cat table is an array, so we will put it in using this notation. It's an array. Now the transition table is a two-dimensional array. The row is, what's the row and what's the column?
Row is state, column is the
Category. Okay. Now we know the new state, and we keep looping. Okay. Now one thing that we need to do is, because when we get out of this loop, we will have an S error. So we want to pop and roll back to the last accept state. So that's why here we need to clear the stack, or clear it if we have an accept state. Sorry. Yeah, clear it if we have an accept. So whenever we have an accept state, so this is like, this is your stack. This is an accept state. Accept, accept, and this is SE and accept. So when you roll back, you want to roll back to this. So you don't want any of these. So once you get to an accept state, you no longer care about the accept states before it. You always, pop the states until you get to the last accept state. So you don't need these. So that's why you can pop the stack, clear the stack. So stack. So it's if state is an accept state, belongs to the set of accept states, then stack clear. And SA here is set of accept states. You can think of this as checking if it's in the set of accept states, or checking if checking a certain flag. Yes.
Why do you have the if statement there instead of right after we set the state?
Not here?
Yeah.
Oh, because we are checking the state that is coming from here. So we have never checked S0 yet. So S0, the first iteration of the loop, you check on S0, right?
Okay, that makes sense.
Iteration number 1, you check S0. It hasn't been checked yet. So you want to do this for S0. Okay. Now, after the loop,
Professor?
you need to, yes?
If we clear the stack, won't we get rid of that start state we were in that said,
Yeah, it's a good question. So we are assuming that, the clear will not get rid of that. Yeah. Yeah, you are right. So we are assuming that this clear is a special kind of clear that will not get, yeah, you are right. So yeah, so maybe we can move this here. And the assumption here is that this is a very good observation. Yes. So the clear does not delete this null state that we have added.
Or just push null back up onto the.
Yes, or you can, yeah, you can yeah, exactly. You can the clear. You can add another null. Now, after we are done with this, we have to check. Then we have to check to roll back. So we have to go back. So we have to keep looping until we get to the latest accept state. So we have to keep looping until we get to either an accept state or to
A null state.
null state. Exactly. So while state does not belong to SA, is not an accept state, and state is not equal to null, we keep looping until we get to a state. And in each step, what we do is state equals stack.pop. And we do truncate the lexeme, which means remove the last character from the lexeme. Remove last character. Remove last character. And roll back, which means, again, move the pointer in your lexeme to the previous character. So when you are x1, 2, 3 equals ABC, back to this example, when you get to this, you need to roll back. So you remove the last character, which is the equal, and you move the pointer to this. So roll back, it means moving your pointer. OK, so then eventually you will get to a state that is either an accept state or a null state. And after the loop, if state belongs to SA, then this is an accept. So we return type of state. So in this case, the type of state is the corresponding syntactic category. So type is the corresponding syntactic category. And if we have multiple types, we have to resolve this. We have to resolve this conflict based on certain priorities. So for example, this type could be identifier or some keyword, and we have to resolve. So what we are implying here is that we are resolving this conflict if the state has multiple syntactic categories. Else, return error that we couldn't match. Yeah.
How do we return the lexeme? So say the parser can tell to see if it makes sense or not.
Yeah. So this is pseudocode. So in order to truncate the lexeme, it means that your lexeme is a string that you are saving in a certain buffer. And to truncate it, you just go back to the previous index in the buffer.
Well, no, I meant when we're doing returning.
Oh, how do you return it?
Yes.
Oh.
We only have one return in a code.
OK, so that's a good question. So in fact, you will see this when you write an actual scanner in the next assignment, not assignment 1, in the next assignment. So it will be saved in a certain variable. So there will be a certain variable that saves the lexeme. And you will see this in the assignment when you use flex. So there is a return value, which is the syntactic category, and the lexeme itself will be saved in a certain variable for holding the lexeme. So because you need both. right? You need both. You need to know that it's an identifier, but knowing that it's an identifier is not enough. You need to know the actual name as a compiler, because the compiler needs to create a variable with that name. Okay? Yeah.
Well, in actual code, something I would do is create a structure, put it in a parameter list with a pointer to it, and then the returns 0 or 1 indicating success or error.
Yes, so that depends on the design of your code and the language that you are using. Yes, yeah. Okay. But again, this is pseudocode, so it's very conceptual. But you will get to write an actual scanner. All right, so this is table-driven. A direct-coded scanner is a scanner that doesn't use tables. A direct-coded scanner is a scanner that does not use tables, but it, in each state, direct-coded. So this is the, it will put, we will not have a loop. And this is going to be our start or initialization code. Then, instead of having a loop, there will be states. This is, for example, state 1. And in state 1, you read the character, you get the lexeme, you push it, but you don't have the tables. So instead of doing the tables, you just directly code the transition by going to the next state. So you say if character equals A, then go to S2. Else, if character equals something else, go to S5, and so on. Then the last else, which corresponds to a character that you are not recognizing, go to what? A character for which there is no transition from S1. Where will you go?
Oh, God.
You will go to SE, or you will go to the end, SE. And if you have a character that you are not recognizing. Now, or let's call it, go to end. And the end is just this. So the end is just this. So you look at, this is the rollback to the last accept state, and then you just do the same thing. So the idea here, the difference between a table-driven and a direct-coded is that here we don't have a table. We don't look up the next transition in a table. We just directly code it. So we just say if the state is S1 and the character is this, go to state S2. If the character is that, then go to S5, and so forth. Now, advantages and disadvantages. This will look ugly, right? This looks ugly and messy, but it's ugly and messy if this is code that you would write manually. This is not code that you would normally write manually. This is code that will get generated by the scanner generator. So this is code that you will never have to debug. So you will not need to debug this code. This is code that will get automatically generated by the scanner generator. You feed the regular expressions to the scanner generator, and the scanner generator will generate this for you with all of these ugly go-to statements. So, yes?
What do scanners generally favor, the table method or this method?
Yeah, so each one has advantages and disadvantages. And I'm not sure, for example, I'm not sure Flex which scheme it uses. It probably uses direct. I'm not sure. but each one has advantages and disadvantages. And in spite of the disadvantages of this, the advantage is what?
No memory access.
Yeah, no memory access. So you are avoiding the memory access, especially the double table lookup. So to avoid memory accesses, you are doing this. And this will be okay if it gets automatically generated. If it's not code that you will have to debug.
One thing I want to point out, though, is that the direct-coded is only for the one language, but a table-driven, just by changing the tables, you can use the same code to scan any language.
Yes, and yeah, that's true. So you are encoding the language within the code, but again, it's automatically generated.
Yeah.
So in practice, you will change the regular expressions. So that's all what you change. You change the regular expressions, you rerun the scanner generator program, and the scanner generator program will generate new code for you.
Yeah.
So you will not have to do it by hand. And like I said, from software engineering point of view, this is terrible if you were to write this by hand. But it's automatically generated.